Hello YouTube, RJ. Hey, today we're going to be talking about the high voltage power supply conversion of the old ammeter, clamp-on ammeter. Third part of this series. If you want to catch it where we are, you can go back and catch the first two. I'll put the links in the description if you have a hard time finding it. Anyway, I'm going to jump over the computer real quick. I'm going to pull up the schematic I showed you in the last video that was going to be what I built and show you what's changed, what I found, where I made mistakes and such, and what I had to do. Okay, let's take a look at the original. This is what I showed you. This is what I created originally, kind of threw together, showed you. And then a couple things happened. One was, went back over it to order parts and stuff. I realized I'd made a mistake right here. These two resistors, which are designed to dynamically load these transistors to make sure that they both take load and not one of them does all of it, is on the wrong side of the transistor. Shouldn't be on the collector, should be on the emitter. So I messed up there, and so I needed to swap that. And you'll see that in the updated schematic here in a minute. After realizing that and making that change, I went ahead and built the circuit. And where here, I'd been reading about 470. This little LR8N is designed to continuously operate at 450 volts between here and here. Well, since you're not going to get to zero here in operation, that gives you a little room. And on top of that, this can actually, the absolute rating is 470. And since I was seeing 470 out of the main power supply, I was assuming that's what I was going to get. And therefore, this was going to be fine. Nothing to worry about. I went ahead and got the power supply end all hooked up. At this point, I was really getting 505 volts. I felt that was too high for this. I needed to get rid of some voltage here. And I decided if I'm going to do that, let's take it to 450 to the rating of the continuous normal rating of this component. So, and that would be unloaded. Obviously, it would go down as we load, but you know, you can turn the power supply on with no load and have it sitting there on the bench. You don't want to damage this. You don't want to have something plugged in and loaded up all the time, or you might damage this. So I wanted to get this down to 450 at this point. And so I thought about it. So what I did is I decided to use Zener diodes. So let me go ahead and close this and open up the new design. So right here's what's changed. Originally, I was going to have two of these 47 volt Zener diodes in here to drop. And I put a little resistor in front of them for the same reason you got resistors here. I want to make sure that they kind of balance, and this will help with that. And so what happened is I put two of them in. I calculated it up. It'd be at full 100 milliamps. We were looking at 2.5 watts on these 5-watt diodes. As I'm sure you're aware, just because it's a 5-watt diode doesn't mean it can get rid of 5 watts. You've got to have a way to get rid of the heat. And so since I don't have a circuit board to put big copper pads on to try to help this, I wanted to lightly load them. So I estimated, little back of the envelope math, that two of these would stay within max operating temperature at 100 milliamps. So I went ahead and built the circuit with these two. And what I found is I was bumping up against 150 C, which is the max normal operating temperature. That's not the absolute, that's the normal. So I was bumping up on 150 C on these two things at 100 milliamps with no airflow for 20, 30 minutes. So I decided that I didn't want to do that. So I added a third to split the current 3 ways instead of 2. And now if I keep all airflow to 0, if I run it for about 45 minutes, it stabilizes out, doesn't seem to move, probably after about 15, 20. But after about 45 minutes, I'm hitting 125 C, which gives me 25 C overhead. And so I'm happy with that. So this is what I did. This drops me down to, it actually drops me down to 450 volts right here. So it works perfect. The reason I knew I needed 2 was from experience in the past. And now I know to be a little more conservative in the future, that, they don't have much heat sink. Now, the difference is, in the past, I've had these on circuit boards and I put nice copper pads, good sized copper pads where the leads hook. And so they have a little heat sink area. And that's where I went wrong. I was not taking into consideration doing point-to-point wiring. I don't have that heat sinking area. The other thing I did was I left the leads. I did not cut the leads, as you'll see in a minute on these diodes. I left them full length. And the reason is the leads are your heat sink. So that gave me as much heat sink as I could get. That I had to take care of. Then over here, notice that these are 100 ohm and I was 10 ohm in the original. That's because I got the circuit built and I found out that I would turn the power supply on and put a little load on it. And both of these would start taking load. You could see them warming up in the thermal camera. And then as soon as they got a little temperature, one would get a little warmer and he'd take off. And this one would cool down, or vice versa. And so you would end up loading one transistor. What it was, 10 ohms turned out not to be enough to do enough drop to force these to follow each other. So basically I increased to 100. That's fine. I've got 2-watt resistors in here, 1 watt. So I'm running these resistors at half their capacity. They're not even running warm, but that did it. These two now take equal load. They're always within about 1 degree temperature of each other on the package itself. So that's working fine. The heat sink's working great, sucking up the power, keeping everything in control. I see these get around 68 degrees. That's comfortable. I mean, that's with 100 milliamp load at low voltages. So that's comfortable for these. That's fine. This is running about 70 degrees C. That's comfortable for that. That's well within specs. So we're not overheating any of this where we really see a lot of heat being generated. So now that's where I'm at. I'm at that point. I've got the circuit to this point right here. I can vary the voltage. Everything is looking good at this point. So we're going to go back over the bench. I'm going to, after I end this video, I'm going to start working on this current regulating circuit. We'll get ready for the meter. Then I'm going to jump, once I've got this circuitry working, I have to jump over and cut the new piece of aluminum for the new faceplate. I'll show you that. We'll talk about that and what we're going to be doing there. So let me jump back over to the bench and okay, so as I explained, I had to drop some voltage. What I did was I stripped this completely out, and let me reach over here so I can grab something. And I was going to use the rectifier diodes that were in there, but unfortunately it's on a card like this and it was taking up a bunch of space. I was going to have so much junk in there that I wasn't going to use for anything. It just didn't make sense. So I went ahead and pulled that out. And I just put a terminal strip in here and used 4007 diode rectifiers as my full wave bridge. Built my own little full wave bridge here. These things are rated for 1 amp at 1000 volts. So that's twice the voltage I needed and 10 times the current. So they'll last forever. So the problem was, I get done with this, I check my voltage, I'm getting 505 volts, as I said in the previous segment. So I needed to get rid of some voltage. So what I did was, this is the terminal strip I put in, and these are those 3 47 volt Zener diodes. And they've got resistors in front of them to help keep them loaded. Works very effectively. They run almost identical temperatures, and that spreads the load out so that a third of the current's flowing through each one of them, and therefore none of them get overheated. Now these things run hot. If you're familiar with high voltage Zener diodes, you know that when they drop that voltage, they generate a lot of heat. These are rated to run continuously at 150 degrees C, so we're talking cooking. I've got them now in the worst case scenario. Bear in mind, the worst case scenario for this would be max current. Max current of 100 milliamps. These are running 125 C. I think I said that in the previous segment too. Sorry for repeating myself, but these are running 125 C after a prolonged no air movement period of time. So I'm very comfortable with that. We're good. They'll last. We'll be happy. So that's what happened there, and that's how I, right off the bat, changes I had to make. Once I got that under control, I have this propped up so you can see a little better. I'm going to flip it over. Before we do flip it over, though, here is our 6.3 volt taps, and so what I'll be doing is I'll be putting some shrink wrap over that and getting it out of the way. The higher current tap here, I'm going to bring up forward. I'm going to run it through the fuse blocks here. I'm going to fuse it properly and bring it out and give us some 6.3 volts on the front panel at, I think this is used in this meter at 2.4 amps. I calculated up. I calculated the filaments of the tubes it's running. I'm going to put a 2 amp fuse in, give myself 2 amps on the front end and say, there you go. You got 2 amps of 6.3 to use for heater elements. So anyway, this will be straightforward. This will be on anytime the unit's on. Of course, 6.3 volt AC is, human safe. So we'll fuse it at 2 amps, bring it up, put it on terminals, banana jacks. Bob's your uncle. You'll have 6.3 on the front panel. So now that I've got my high voltage dropped to 450 volts, I started building the regulation circuit. None of this is neat, I'm going to tell you now. I didn't intend to try to make it neat. I wanted to do this point-to-point wiring just to kind of keep it in the spirit of the way the old meter was built, and just because I don't typically do it. I use built circuit boards, so I thought, yeah, do something different. It's not neat. I still got some cleaning up to do. I've got a couple little extra leads here I got to clip off and get rid of, but it's not neat. It's not intended to be, but let me prop it up where you can see it a little better. let me look over here. Pardon my looking away. I want to see what it looks like, what you can see. I think I'm going to hold it up here a minute for you. So what you're seeing is, of course, I've mounted a good size heat sink in the case. I've got my 2-tip 50s. I've got some isolator mica shims to make sure that they're isolated electrically. I brought them out to their own terminal strip. And so on that terminal strip, you just basically have 3 legs of each one. And then what I have is I have the high voltage coming in. Here is wired over to the collector on the transistors. Then on the emitter, I've got those 100 ohm resistors bringing out and allow my high voltage output. Now, this is your little LRN8 TO92 little unit. And I've got the 1N4007 diode here as protection that I showed earlier to protect if the voltage on the output side happened to get higher than the input. I don't want to blow that up, so that will bypass it. So with that, really all you have then is, you've got it wired up where you've got the voltage coming in, the output voltage going over to the bases of the BJTs, and you've got the adjustment pin of this wired in with a couple resistors as in the schematic, and your 10-turn variable pot, and that controls the voltage. And so far that's where I'm at. The next step is to build the current regulation circuit that allows me to cap it at 100 milliamps if you dead short it no matter what, and also let you turn it down. I will tell you the simulation was pretty well dead on this. As I remember, the simulation showed I was going to be able to go down to about 73, 75 volts, something like that, just under 80 volts, all the way up to, like 440, 430. And I am indeed getting, if I got a low load, I can get 440. As I go up in load, it's less. I think I'm going to be able to do 100 milliamps about 400 volts. So I should be able to do about 73 to 400 volts across the full 100 milliamp range. So I'm very happy with that. I think that's great. So that's kind of where we are. This video is not going to be long. I just wanted to catch you up. It was just where are we? Now, what's the next step? Well, let me grab something. Okay, here's the faceplate off of this. As you can imagine, we're not going to be using this. I bought a piece of aluminum, so once I get the current limiting circuit working correctly, I'm going to take my new piece of aluminum I bought. I'm going to clamp this down and screw a couple screw holes in it, tighten some screws in to lock it together. I'm going to take a jigsaw and we'll cut out an exact replica of the outer perimeter of this. End up with this shape with my hole in place. Then I'm going to drill holes for my controls where they're going to go on the layout that I've done up. And I went over and created artwork for this faceplate. I kind of laid out, figured out where I could put things. You have to remember there's structure going through here, so you just can't put your pots and your switches and your banana jacks. You just can't put them anywhere because you'll run into these. So I had to kind of do layout work, figure out how I could lay it out and get what I want. And I've done that. And so once I've done that, I create artwork for stenciling. And then what I'm going to do is, before I drill any holes or anything, I'm going to put the stencil, I'm going to paint it, put the stenciling on, stencil it. It'll all be black letters. It's going to be a lighter color than this. I picked kind of I don't know what they call it. I'll show it to you. It's, see what color it is. Shell white, it's called. It's an off-white. The wife and I kind of looked at it and thought this would be a nice color. And I just think I'm going to like this. Decided to go this. That way my black and white gauge will kind of look more in place. So that we're going to put a coat of this on.
Okay, guys, just a short little, sorry about the audio quality. I'm in the craft room here, just recording on the little pocket. And what you're looking at is the laser. I decided to try something different instead of silk screening this time, since I was doing black. I went ahead and painted the panel. You're looking through an amber laser safe glass, so it's not, colors are not right, but I went ahead and took my graphics I was going to create a silk screen out of and threw it in the computer in the craft room and fired up the laser, swapped the head over. This particular laser head you see here is the infrared one. It's designed for etching metal. The other, the what they call the blue laser, that's what the normal, when you want to engraven wood and things like that. This is the metal head, the infrared wavelength. And it's very slow, but man, it's doing a fantastic job. Look, the resolution is really good. I think this is going to turn out great. Of course, you'll see the final product, but I think this is a much higher resolution, much clearer. Those thin lines are really defined. Silkscreen has a hard time with that kind of real thin stuff. So I'm pretty excited about this technique. This is going to add a whole new technique to me for doing panels and stuff. This just kind of popped in my head. I hadn't seen anybody do this particular way. So
anyway, that's where we are. Hopefully in the next video, I'll have this thing pretty well wrapping up, be able to put it through the rigorous test. Like I said, I've done a little thermal, watching it for some thermal, looking at, how it appears. I haven't looked at it from a wavepoint point of view of, what my ripple is, how well it regulates yet. That's because there's some capacitors still need to go in. I want to get that current regulator circuit in there first. Maybe we'll do those tests and stuff on the next video, show you where I ended up. We'll put it through the paces and we'll see if my design is worth a darn. Is the power clean? Does it regulate well? And does it do what I intended it to do? So, hey, thanks for tuning in and checking out where I'm at with this. Appreciate you going along for the ride. But most of all, hope to see you in the next video.